Through our research, we found that prolonged exposure to certain perfumes can have harmful side effects, such as kidney damage, as well as being linked to causing pancreatic cancer. Thus, the goal of our lab was to create a perfume which would be less volatile, and thus would reduce the exposure time to those around the perfume and reduce the chance of harming them. So our lab focused more on organic chemistry, specifically esters. Esters are produced in a reaction between a carboxylic acid and an alcohol, in a reaction known as esterification. Esters are known for their pleasant fragrance. Since we have access to a huge variety of acids and alcohols, we can have esters that produce different scents. Sometimes only small changes are needed to get a completely different fragrance. While there are an infinite number of combinations of acids and alcohols, we have selected some of the most distinct fragrances. Since the reaction between a carboxylic acid and an alcohol is very slow, adding sulfuric acid as a catalyst will speed up the reaction. Esters are common in organic chemistry and biological materials, and often have a characteristic pleasant, fruity odor. This leads to their extensive use in the fragrance and flavor industry. Esterification is a reversible reaction. Hydrolysis, which literally means water splitting, involves adding water and a catalyst. As a result of this reversibility, many esterification reactions are equilibrium reactions. Esterifications are among the simplest and most often performed organic transformations. The purpose of our perfume lab is to determine the number of carbons in an alcohol that will create the least volatile perfume when it is combined with a carboxylic acid. For our lab, we had 4 25 milliliter round bottom flasks, magnetic stirring bar, graduated cylinders, paraffin wax, pipettes, a hot plate, sulfuric acid, sodium bicarbonate, and 2 milliliters of isoamyl, octyl, benzyl, and butyl, as well as 3 milliliters of carboxylic acid.
To do this experiment, we used a graduated cylinder and we measured out 2 milliliters of an alcohol. Using another graduated cylinder, we measured out 3 milliliters of carboxylic acid. We then prepared a flask and added in the measured alcohol and carboxylic acid, along with a magnetic stirring bar inside the flask. We then carefully added in 10 drops of sulfuric acid and then wrapped paraffin film around the opening of the flask to prevent the smell from leaking into the classroom. We then placed the flask onto a hot plate and turned the temperature to 45 degrees Celsius and turned the stirring speed to 3. We left the flask on the hot plate for 3 minutes and then carefully placed the flask into an ice water bath to allow the reaction to cool down for a few minutes. We then repeated the procedure with other alcohols. And then we had a smell tester stand 10 meters away from the flask, and we removed the paraffin wax off of the flask and have the smell tester walk towards the flask until they can smell the ester. We then recorded data and repeated for all the remaining esters. With 4 carbons, the distance of smell was the furthest, 124 centimeters. With 7 carbons, the distance of smell was the second furthest, 77.9 centimeters. With 8 carbons, the distance of smell was the third furthest, 30.1 centimeters. With 5 carbons, the distance of smell was the closest, 20.8 centimeters. There was no correlation between the number of carbons and distance it smelled. The graph shows that there was no trend in relation to number of carbons in the ester and distance that it was smelled at. This matches the lack of a trend in the data table. The graph begins at 4 carbons in an ester, as we didn't collect data on esters with fewer carbons, and that value is the peak of the graph. The graph then steeply declines to 5 carbons in the ester, as the distance at which it smells is the shortest distance. The graph then inclines when there are 7 carbons in the ester, before declining once more when the ester contains 8 carbons. The purpose of our lab was to mix alcohols with different numbers of carbon atoms in them with a carboxylic acid to determine effects of carbon number on distance scent would be detected. An important part of our procedure would be to react the alcohols with the carboxylic acid. In order to do this most easily, we left our procedure with generalized terms such as alcohol and carboxylic acid, such that we could use whatever substance was available at school. The sulfuric acid added in step 4 of the procedure acts as a catalyst to speed up the reaction. Placing the paraffin wax over the flask ensures that the scent of the ester does not escape prematurely, as early exposure to the scent could result in the scent tester becoming used to the smell, resulting in incorrect data collection on the distance at which the scent was smelled. The heating and stirring of the solution in the flask serves to increase the amount of movement of the molecules, causing them to collide with one another and react at a greater rate. The temperature designated for use was 45 degrees, as lesser temperatures resulted in the reaction rate being increased to a lesser extent, and the greater temperatures resulted in gas causing the paraffin wax cover to pop off. Speed 3 was chosen for the magnetic stirring bar, as greater speeds caused the solution to be splattered on the sides of the flask, removing some of the reactant from the reaction. 3 minutes was used as the time allowed for the reaction to occur, as we found that the solutions could react fully in around that time. Placing the flask in ice water cools it down, enabling us to handle the flask more easily. Having the smell tester stand 10 meters away provides a barrier of distance which the ester scent could not cross, and thus enabled the smell tester to accurately determine at what distance they smelled the ester. According to the data we gathered, there is no correlation between the number of carbon atoms in an ester and the distance at which the scent of the compound is detected. This differs from our expectations, as we expected there to be an increase in the distance which the scent would be detected as the number of carbon atoms in the ester increased. However, this did not occur, as in the data it can be seen that in butyl ethanoate, which had 6 carbons, had the greatest distance at which it could be smelt, as opposed to octyl ethanoate, which had 10 carbons but was smelt at the second shortest distance. This relates to our research, as we did not find a large discussion on the effect of the number of carbons on the distance the scent traveled. The chemistry observed in our lab was the formation of esters. This occurred through the removal of a water molecule, taking the hydroxide from the carboxylic acid and the hydrogen from the alcohol. This creates an ester compound. Here, the property of the compounds, namely the ester bond formed between the carboxylic acid and the alcohol. This property suits its function, which is to produce an odor. It is the ester bond which accomplishes this desired function.
One of the errors of our lab was that we may not have left the flask to heat for a long enough period of time. This would cause the alcohol and the carboxylic acid to have an incomplete reaction to produce esters, thus affecting the distance that the scent could travel. It affects the distance the scent could travel in that the reaction would not completely occur, and thus there would not be as many ester molecules to produce the scent. The aroma may also be different than what it should originally smell like due to the unfinished reaction. Another error that may have occurred during the lab was that the group members may become accustomed to the smell. This would happen as we were all working on the lab, and some of the scent may have escaped from the flasks, thus resulting in us getting accustomed to the smell. This would lead to us not being able to accurately detect it during the smell test, and creating incorrect data. Another error that could have affected the lab was wind. Even the slightest gust of wind may really affect the distance that the smell could travel. Thus, the distance that the smell could travel could be further or closer than what the data stated. Improvements to this experiment could be doing more tests prior to the actual lab in order to determine the best time to fully react the alcohol and carboxylic acid. In order to accurately determine when the scent could be detected, Perhaps a period of time could be taken between the lab and the actual test in order to clear out the nose with fresh air, thus removing any possibility that the scent tester could have become accustomed to the smell. A solution to the variable of wind would be to find a separate, enclosed room that no one else would be in and would provide enough space for the scent test to occur. From this experiment, the most important thing we learned was that different alcohols and acid can produce specific smells according to the number of carbons. However, we learned that the number of carbons does not affect the distance the scent travels. In conclusion, and in relation to the purpose of this lab, it can be stated that octyl ethanoate is the ester which is the least volatile, as it was smelt at the closest distance.